morning now.
Good morning, ladies and gentlemen. Let's go ahead and jump into this. We've got 3 resistors, and they're all connected in series across a 30-volt battery. Go ahead and draw this in your notebook.
What would that look like? We're not asking any questions, just can you draw a series circuit with a 40, a 10, and 25 ohm resistors across a 30-volt battery?
Okay, so we said 30 volts.
30 volts.
30 volts. And then, what goes on?
45.
What was the other one?
10, and 25.
And 25.
Now the way she's got this drawn is one way to do it. There are a million different ways to do it. As long as there's only one path for current to follow, any way you got it's going to be good.
They could be anywhere as long as they're in that path.
All right, let's take a look at some important characteristics.
Okay, so in a series, I kind of drew this kind of thing. In a series circuit, there is only one path for current to follow. The current is the same at every point. So no matter where you put that ammeter, if you were to put it here, 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 or here, it would all be the same.
Yep.
So I could put it here. It's going to be the same current as here, as in
And we
here.
did a lab where we proved this. Now, and the important thing about this is the electrical current moves like a bicycle chain. It goes around. It's not like one electron goes all the way around and another one comes through. It's like they all move around in...
kind of like that PhET simulation that you guys were playing with. They're all...
That's right. That's right.
Okay. Alright. Loop rule. What is the loop rule? So the potential... Sorry, my stool's in the way.
Sorry.
The potential drops across each element add to equal the potential increase of the source. We've heard this before, right?
Yeah.
So what that just means is that the ups equal the downs, and we're giving it a name. It's called loop rule.
Yeah.
So go ahead, Boykin.
What will be the equivalent resistance of this? You just add them up, don't you?
Yeah,
45,
10
55,
so 45, 55, 65, 75, 80.
80. So you have an equivalent resistance of 8. Why don't you just draw that equivalent series circuit over here on the right?
Sorry.
Do it over here, and
Yeah.
then that way we can actually...
Yeah, so what does this look like? What does the battery see? That's what Mr. Boykin always says, right?
Battery's stupid.
Okay. The battery sees, we said 85, 80?
80 ohms
80 ohms?
and
30 volt
30
battery.
volts. So what's that current going to be, boys and girls? It's going to be the V equals IR. I is V over R. That'd be 30 divided by 8. 30 divided by 80. 3/8.
3/8?
That's going to be about 37.
We get 30 divided by 80. Let me not be lazy. Okay, same thing. I was like, I think it's the same thing. We'll call it 0.4.
0.4. So you got
Make it
0.4 amps. So we can calculate what the voltage drops across each one of these are. So let's do the 10 ohm first.
Yeah.
If you had a voltmeter over the 10 ohm, that'd be the current times the resistance, 0.4 times 10, that'd be 4 volts.
0.4 times 10 is...
Mr. Boykin's clever. He did one he can do in his head.
4 volts. 4 volts, right?
And then let's do the 45. That's going to be 0.4 times 45.
4 times 45. You guys
I can't do that in my head. I'm too stupid.
0.4 times... I got an X now. 0.4 times 45. I get 18.
18. Now, what does the loop rule tell us about the 25 ohm resistor?
Well, it tells us that the ups have to equal the downs. So, it tells us that the drop over here, here, and here have to equal the
18,
increase here.
18 plus 4 plus what equals
18,
30?
19, 20, 21, 22. That's going to be 8, right?
That's 22 volts. That's 8.
Okay, because
volts.
this plus this plus this gives me...
It's a simple thing. It's profound, and it rules electrical circuits.
Rules the world. Okay. All right, so parallel circuits. Parallel circuits have more than one path for current to follow. More paths equal more current.
You want to draw a parallel circuit?
Yeah, let's do it.
So boys and girls, you draw a parallel circuit with a 45, a 10, and a 25. while we're doing it, you go ahead.
It's more, how do I know what it looks like? I don't know. It doesn't really matter. The blue, it's getting a little bit better to erase. Okay, so let's go ahead. We'll go boop, 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 okay. Okay, and we got, what is it? 10? Wait, I want the colors. I like the colors.
10, 25, and 45.
10, 25, and 45.
No, yeah, 10, 25, 45, and a 30-volt battery.
And then a 30-volt battery. Okay. All right, so let me go to my next thing. Is there anything else in there? That's all.
Yeah, well, there's the potential across each element is the same because both sides have access to the battery. So you got 30-volt battery.
Yeah.
There's 30 volts across each resistor.
Should I draw that in real quick?
It'd get pretty messy pretty fast.
It does get messy. On my homework, I drew it in there.
All right.
So, if I put a voltmeter here, here, and here, it would say 30 for all of them.
That's right.
Right? That's what it means.
And we actually did that in a lab.
Yeah. Okay. And the junction rule. Oh, the junction rule. Okay. We've seen this before. For any junction in a current, the total current into the junction is equal to the total current out of the junction.
Miss Moore, let's find the equivalent resistance of this parallel circuit. Can we do that?
Yeah, let's do that. So, wait, did you want to
Well, we'll get to this in a minute.
Okay.
We'll use that.
All right. So, what is this going to look like? Well, it's going to reduce down to just 1, right?
Yeah.
Okay. So, how do we figure that out? What is it going to be?
Well, it's the inverse relationship. It's 1/10 plus 1/25 plus 1/45. And remember, there's a button on your calculator that does that. It's the x to the -1 button.
Okay, so 10, it's squared. Delete. 10 to the -1 plus 25 -1 plus 45 negative. Oh, I forgot to do 45 -1. -1. I said it didn't do it. Okay. Are we done?
No, what it gives you a number that's the inverse. You got to hit x to the -1 again.
We'll call it 6.
6. So
6 ohms.
So we got a 6 ohm resistor.
Okay, so this is going to be.
That's the equivalent resistance and 30 volts.
Oh, yeah.
What's the current flowing through the battery?
30 volts.
Let's see, V equals IR. I is equal to V over IR. 30 divided by 6.
Is 0.5? 0.5 amps?
No. It's going to be more.
Oh, sorry. 30 divided by 6. I put 60.
30 divided by 6.
Okay.
It's 5 amps. So we got 5 amps. And down here on our one on the left, put an ammeter by the battery. 5 amps.
Oh, let me see. 5 amps right here. Okay. So let's go back to our junction rule here.
For any junction in a circuit, the total current into the junction is equal to the total current out of the junction.
Okay.
So the current leaves the battery and hits that first junction there at 45 ohms.
Conventional current. Sorry, keep going, Wigan.
Okay, how much current is going to flow through the 45 ohm resistor?
Can we calculate that?
Yeah, it's just V over R.
Yeah.
That's going to be 30 divided by 45.
30, yeah. 30 divided by 45.
I think it's going to be 1.5.
I think you're right. No, 30 divided by 0.6. We'll call it 0.7.
Oh, you're right.
I know.
0.67.
0.6. You want to call it 0.67?
Yeah, and put a little ammeter right here.
Yeah. Okay, so this is point. You know what? I'm gonna call it 0.7 just so it's easier.
Okay, 0.7. I like that. 0.7 amps.
Okay.
So you got 5 amps here. 0.7 goes that way. How much goes up?
How much has to go here? We're gonna call it
4.3. Well, yeah, 4.3. That's good. How much current's going to go through the 25 ohm?
Well, let's figure it out. So we'll do our voltage, which is 30 divided by 25 this time. Okay, 30 divided by 25. You guys with me on that math? I hope I don't have to write it out. 30 divided by, is that right? Yeah.
Yep.
Okay, and I get 1.2.
1.2.
Okay, so right here, this is 1.2 amps.
Okay, so boys and girls, we got 4.3 amps going into this junction. 1.2 go that way. How many go through the 10 ohm?
So 4, is it 3.1? Is my math good?
Yes.
3.1, yeah.
3.1 amperes.
Okay.
And so, and we can confirm that.
Oh,
Well,
by
but-
doing the math we wanted to.
Well, what you'll have is you'll have
Oh.
30 divided by 10, you
Which
get
is
3.
A little off.
But-
That's because
well,
we've been rounding.
Rounding issue. So, and does that make sense? You've got the least resistance, the most current, and the most resistance, the least current.
That makes sense. Okay.
That's the junction rule.
Woohoo! We've got a fancy new name for what we've been doing the whole time. Okay, compound circuits. So they combine series and parallel elements.
In the real world of electronic devices, circuits are very seldom as simple as what we're playing with. Some of them are insanely crazy. We're not going there, but we will look at some complexity.
Come on, Blue. All right, so I'm gonna go ahead and draw a compound circuit for us. Yeah.
All right.
Okay, so we'll do a resistor right here, a resistor right here, and then a resistor right here.
Okay. All right, where is the parallel part of this?
So this right here is my parallel circuit,
Yep,
and then this is in series.
that's in
right here.
series with a parallel. So here is a compound circuit.
So so the first thing we want to do is simplify it, right? So how can we
Let's
simplify
put some numbers in here.
Oh, yeah.
Let's go back to our
Should we do our
10,
regular stuff?
25, and 45.
Okay, and a 30-volt battery, right?
Yeah, 30 volt battery.
30 volts. And this, let's call it, we'll say 10. Well, this one's the dark one. 25 and 35, right?
Yeah.
Okay.
All right, so we want to simplify the compound circuit step by step until you have one equivalent resistance to find one current. What should we do first here?
Let's go ahead and collapse this parallel.
All right,
here.
so-
so first, what will it look like, right?
Well, yeah.
Okay, so if I mesh these into one, I'm just gonna have one right here, right?
uh-huh.
So it's gonna look like this, and I can't. This one, we haven't done anything with that yet, so we just have to draw it right
Yeah,
there.
so that one's still going to be 35 ohms.
Okay, but what is this one over
Or
here?
40, is it 35 or 45?
Uh,
35 ohms.
is it
35,
35?
that'll work. But now we need to figure out what the parallel component's going to be.
Okay, so how do we do that? It's in parallel, and we want their equivalent resistance. That means we do.
The inverse, 1/10 plus 1/25.
Okay, so 10 to the -1 plus 25 to the -1 gives me my answer. I take it to the -1, and I get 7.
So that's
7
7 ohms. And you know that's a good answer because it's less than either of the ones you started with. Okay, so now we have a series circuit. We have to simplify that.
Okay, so this will be pretty simple, right? So the series ones are just so easy. Okay, we just want to simplify it into down to one equivalent resistance. We just add these together, right?
Yep, 35 plus 7.
That's gonna be 42, right?
42 ohms.
42 ohms.
And
Okay.
30 volts.
Oh, and I forgot my voltage. 30 volts. There we go.
All right, so what we've done is we've simplified the compound circuit step by step, and now we have one equivalent resistance. Now we can find the current. You cannot tell what the current is from this original thing. You just can't do it.
It's not a thing.
V equals IR. I is V over R.
So it's gonna be 30 divided by 42.
Yeah,
So 30, I think we did this already. I think it's 0.7, right?
I don't know.
Wait, we said 30, yeah, voltage divided by 42. Okay, 0.7.
0.7 amperes.
0.7.
And what I would like to do is go back through and put an ammeter in every one near the battery, 0.7 amps.
Is that right? Or do you like to put it right here?
No, that it doesn't matter. It's a good place.
Okay.
All right. Okay, now we've got the current.
All right, sweet.
Okay, what's the next slide?
Okay, so I think our next slide is work backwards to find any expected values.
Well, what's the voltage? What's a potential difference across that parallel part of the circuit?
Wait, which one, Wigan?
The 7 ohm.
Oh, right here? We want to figure out the voltages? So if we want the voltage, so we know our we've got 0.7 amps for our current, and our resistance here is 7 ohms, right?
Yeah.
So
7 times 7 is 49. It'd be 4.9, I think.
Yep, 4.9.
So 4.9 volts.
Volts, I apologize. So 4.9 volts right here. And then
What's
can we
the
do same
voltage
thing?
going to be across the 35 without doing Ohm's law? No
Oh,
calculation.
sorry, yeah, we can just add it up together, right?
30, let's see,
4, 5,
4.9
6,
plus what equals 30?
2.1? Is that 2.1?
No, 49.
Oh, sorry, to 30.
30
right, right.
minus 4.9.
30 minus 30.
25.1.
26. What is it?
25.1.
25.1, is that right?
So the voltage across here is 25.1. That's the loop rule.
0.1 right there.
Okay, so now, what if our question was, what is the current through the 10 ohm resistor on the original circuit?
Oh, over here.
If we want to know what the current was, we know the voltage because it's, we just calculated it's 4.9 volts across that parallel part. And we've got the resistance, V equals IR. I is equal to V over R. So we've got 4.9 volts.
Right here? Wait,
Yeah.
Wait,
See, this resistor right here
Yeah.
is 4.9 volts. That's the parallel.
oh, okay, yeah.
So across the
It's
parallel,
gonna
we
be
have,
4.9 for both of them. I see what you're saying.
Yeah.
Okay. And why are they the same? Well,
because it's parallel.
yeah, it's parallel. They see the same thing. Okay, so, and then are you saying let's calculate the current through there?
Let's calculate the current through
Yeah.
the 10 ohm resistor.
Through the 10 ohm resistor. Here we go. So current equals V over R. Okay, so voltage is 4. Oh, I forgot my units there. Voltage. 4.9 volts divided by 10 ohms. That's going to be
0.49
amperes. Okay, so
0.49 amperes. Now, how much current's going to go through the 25 ohm resistor?
well, whatever. Let's 0.7 divided by
0.7
that.
comes in, and 0.49 goes out.
You got that, Mr. Boygan?
Well, 7 minus 4.49, that's going to be
I get
2.1?
0.21.
0.21, yeah.
0.21, yeah.
0.21
0.21
amperes.
amps.
See how this stuff works, ladies and gentlemen?
Okay, it's making sense.
So you start with your diagram. What we did is we had a parallel thing, we collapsed into an equivalent resistance for that. Then we've got a series, we collapse that and define this equivalent resistance for the entire circuit. Then we found the current, and we were able to work backwards to find any number of things.
And so it's really important that you realize that this is not the current here, right? Like these things, because of the junction rule, the current isn't going to be equally distributed here in this
Yeah,
parallel
that
circuit.
0.7 amps
Right.
is shared between those two parallel resistors.
That's the junction rule, and then we know that they're each seeing the same amount of voltage from the batteries.
How we doing, boys and girls? You got
I
this?
think we're doing.
Are we going too fast?
Yeah, they're fine. Okay. So for homework, I didn't add a slide on here. For homework, you guys are gonna do page. What page was it? It'll be page number 64, 65. It'll be page 574. Wait, no, I lied.
575.
575, number 64, and 65. And then if you turn the page,
Well, that- okay, yeah,
okay,
and
and number 70 on page 576.
that looks like the one we just got through doing.
Okay.
Okay, so now just a little hint on this. Notice you've got a series here, and then that's in parallel, and then a series here that's in parallel. And so there are several steps here.
And it says it wants to find the equivalent resistance between the points A and B in the drawing. So that means it wants you to reduce it to just like one
resistor.
It's a fragment. It'll end up being looking like a fragment, right?
You'll be doing iterations.
Yes, yes. All right, and then same thing for number 65. And I don't think we had anything to add for number 70.
What is it asking for?
Determine the power supplied to each of the resistors. You told me
Power is current times voltage. So you'll need to find the current through each resistance and the voltage across each resistance.
Yep.
So, can you do this?
Good luck.
Bye.